So hi, my name is Vishnu and I'm a PhD student at Chalmers University of Technology in Gothenburg, Sweden. And I'm also working with Tech for H2 Competence Center. We focus on multidisciplinary research within technologies and innovations for hydrogen. And the work has been done in close collaboration with our industrial partner Siemens Energy and funded by the Swedish Energy Agency. So I'm going to talk about what we did with stainless steel 321 in use for gas turbines. My colleague Franz mentioned how an industrial gas turbine works, but I will skip through it pretty fast. That basically you rely on the thermal energy conversion of a chemically reactive fuel to create electricity. So one interesting part about gas turbine is it offers very high fuel flexibility. So you could find gas turbines that run on diesel, gas turbines that run on natural gas. What happens when you combust hydrocarbons is that you produce carbon dioxide, and of course we would want to reduce it. So my project deals with what can we do to enable hydrogen combustion in conventional industrial gas turbines, which are not originally designed to combust hydrogen. So we were talking a lot about fuel supply through pipelines, and then it actually ends up in these turbines located at different stations across Europe. And then we would want to make sure that the turbines that were originally not designed against or handle hydrogen does not fail. So what we do is validation of stainless steel 321. Since conventional selection process when these turbines were designed didn't take into account the amount of delta ferrite, but now this is going to change, especially when we want to combust hydrogen. We would like to investigate the effect of delta ferrite 321. It's commonly used for fuel supply system and exhaust system in turbines. So we have a stainless steel 321, and what is peculiar about 321 is it comes with addition of titanium in it compared to a 304. So it is better resistant to corrosion as well as better weldability. So the methodology that we use for this study is hydrogen charging in recharging in a pressurized autoclave for sufficient time to saturate the specimen. Then we found that the hydrogen concentration was increased to about 21.5 weight ppm. Subsequently, did in situ pressurized testing. Tensile testing was done at ambient temperature, and then low cycle fatigue testing at both ambient and 120 degrees centigrade. And I'll come shortly to why this 120 degrees centigrade matters for such metastable stainless steel. So tensile testing was done with standard ASTM spec geometry in situ pressurized chamber. And we can clearly see that the reduction of area and the uniform area reduction that hydrogen did embrittle the alloy. So of course, the next question would be, how does a fracture surface looks like? And we see a completely different morphology with parallel cracks running across the cross-section along with the transgranular cleavage. And these parallel cracks are basically delta ferrite interfaces with enriched chromium and depleted nickel. This is also confirmed with cross-section analysis along the longitudinal cross-section, where we can clearly see the crack is growing through the interface, while we don't see such an effect in air. And this effect of delta ferrite is also seen in the ability of the material to plastically deform, thereby decreasing the amount of martensite transformation. So it significantly affects the strain hardening capacity of the alloy. So just to summarize, so we did find that hydrogen affects or attacks delta ferrite interfaces, thereby affecting uniform ductility as well as strain hardening response. As we move on to low cycle fatigue, we did low cycle fatigue strain controlled at 6% per minute strain rate with standard LCF test geometry. And what is peculiar about this 120 degrees is basically in metastable stainless steel, which are susceptible to deformation-induced martensite. You increase the test temperature, you see an exponential decay in the amount of martensite. And of course, it's very easy to think that once you have lesser martensite formed, your embrittlement is just going to disappear. But what we see here is that you have embrittlement both at room temperature as well as at 120 degree when you test with hydrogen. So when we jump into fracture surfaces, we clearly see a very big difference in low cycle fatigue fracture surfaces when tested in hydrogen gas. We see the residual zones to be very similar to that of the tensile tested specimen. But also what is peculiar is the lack of fatigue striations, which could also be literature which clearly mentioned that hydrogen affects the blunting. This is also very similar to what we see at 120 degrees, pretty much exactly same with lack of striations, but presence of striations in air. This is again indicates that even at lower martensite content, we still see a significant amount of embrittlement like we see at room temperature. So it is of course interesting to quantify what's the amount of martensite at 120 degree, because it won't go away completely because it's not above the MD temperatures. We did effect of LCF test temperature. We did large area EBSD maps to quantify the amount of martensite. And you can see it is the amount of martensite, not the BCC. We try to distinguish delta ferrite and martensite here. And you see that at 120, you clearly see a decreased amount of martensite transformation, as well as, but what is even more interesting is that when you consider the hydrogen tested specimens, you see a drop in the amount of martensite formation. And this is not something not expected, but we expected it, but because in hydrogen, you run lower number of cycles, and then in LCF, you have plastic strain accumulation in each cycle. So lower number of cycles, that could also mean lower. But what is interesting is that 120 degrees with even low martensite content, your fracture surface looks extremely similar, and the embrittlement is even worse as compared to room temperature testing. So we know that there is something else in the material that is causing embrittlement, even at lower transformation. So let's come to summarizing. So we find that delta ferrite is predominantly held responsible for embrittlement at 120 degrees centigrades, even with lower transformation of martensite. And we see that when you test at 120, you slightly see an improvement in life because of retarded martensite. But if you have delta ferrite in your material, it is going to embrittle. Conclusions is basically we find the effect of delta ferrite to affect the embrittlement both at room temperature as well as at 120 degree low cycle fatigue. And that such materials used in traditional conventional gas turbines needs to be examined further. Possibly would be nice to replace it with 321 free of delta ferrite, or maybe even better option is to get a good 316L. I would like to acknowledge the partners in the project.